Alright, so as we start to talk about reaction mechanisms, what we want to do is we want to step away and stop looking at things at the macroscopic level where we're measuring concentrations and start to think about what's happening at that molecular level and what kind of reaction steps are undergoing. So, what we're doing for a reaction mechanism and how reaction mechanisms are strange is that with a reaction mechanism, you can propose there's a reaction mechanism. You can never really prove it's right. You can only disprove it with a kinetics study. So what we want to talk about here is what steps occur for a reaction to go. So we're going to talk about two different types of reactions. There's going to be an elementary reaction, and an elementary reaction should make sense because it just means that there's a single step that occurs. So the other thing that we'll look at are overall reactions, and this is what we've been looking at so far. Like this will kind of have some similarities to what we were doing in Hess's law in thermochemistry. So we're going to look at individual elementary steps and then an overall step. So we're going to figure out how we can use these elementary steps to write a rate law for an overall reaction. So an overall reaction, again, is just the combination of all of these elementary steps. So here, what we have is we have our overall reaction of NO2 reacting with carbon monoxide going on to form NO and CO2. So what we're going to do is there's a proposed mechanism for this, and the proposed mechanism is that two NO2 molecules smash together, and upon that collision, they form one NO molecule and one NO3 molecule. Then from there, we have an NO3 molecule colliding with a CO molecule, and that forms an NO2 molecule and a CO2 molecule. So notice that not everything that appears in the elementary reactions is in the overall reaction. So here what we find is that our first piece that disappears is, so we have two NO2 molecules colliding and forming NO3. So this NO3 cancels out with this. And then one of our NO2 molecules cancels out. So then we end up getting our net overall reaction up here. So whenever that happens, we're going to start to look at the elementary reactions and try to propose what's happening at this molecular level. So here's the schematic. So what we'll see is, here we have those two NO2 molecules. These are going to collide. And then after they collide, and if they have enough energy, what we can see is that in this case, we could actually knock an oxygen off and then form NO3. So we have colliding molecules in our reactants and then molecules that are separating away in the products. And then our second elementary step is, again, the collision of these molecules. And then them separating again. And then this should be, let's see, that should be NO on this side. I think I made a mistake. Yeah, that should be NO instead of NO3. So there should be another oxygen here. All right. So, but we're just talking about reactants colliding together and then products separating apart. Well, what do we call those species that don't appear in the overall rate law or in the overall reaction? Well, we call those intermediates. So intermediates is a molecule that's generated in one elementary step but then consumed in another. So that example of that would be NO3 in this case. So we formed NO3 right here, and then it was consumed in the very next step. All right, and then I just completely screwed up this picture, so we'll talk about that in class one day. That should be NO2 over here. Okay, so whenever we talk about these collisions, we talk about this term molecularity. So molecularity, I know it looks like a made-up word, but I promise you it isn't. It refers to the number of molecules or the atoms in the reactants. So if you have one molecule decomposing, so there's only one molecule that's required for this reaction to go, we would call this a unimolecular reaction. An example of a bimolecular reaction, so here, is whenever bi means two, so two molecules collide together to form your products. So what we'll see is that unimolecular and bimolecular tend to be more common for elementary reactions, but every now and then we'll see a termolecular. So this means there's three molecules or atoms that are hitting each other at the same time. And if you think about this, if you're thinking about either two people running from opposite ends of a football field and then trying to collide with each other, that's going to be much more common than three people starting independently. So it's one thing to have 2 points hit each other at the exact same moment, but then if you throw in a third point and then you try to have them all hit each other at the same time, it's going to be much harder for that to happen, for that reaction to go. So then as you get even higher order, you're not going to see something with molecularity of 4 or 5. It's just going to be very, very difficult. It's hard enough to get two things to hit each other perfectly and have enough energy to go on to form products. So, well, what can this molecularity do for us? We can actually start to predict reaction mechanisms from this. So let's go ahead and start out with this example. A suggested mechanism for the reaction of NO2 with F2 is the following. So we have NO2 colliding with F2 to form NO2F plus F. So the first thing we want to do is consider that's step 1, and step 2 is NO2 plus F goes on to form NO2F. Is let's write the overall reaction. All right, so what we'll go ahead and do is we'll start with NO2. Okay, well, there's 2 NO2 molecules on the left-hand side. There's no NO2 molecules on the right, so it does not cancel out. So our overall reaction is going to start like this. We have 2 NO2 plus, all right, the next reactant, let's go ahead and consider F2. Well, I don't see any other F2 molecules in the reactants of either step 1 or step 2. And I don't see it in the products. So F2 must be a reactant in the overall reaction. Let's go ahead and look at F. Well, F's in the reactants over in step 2, then it's in the products in step 1. So these two cancel each other out. So F will not appear in the overall reaction. And then, as we continue to look on, we have NO2F in both step 1 and step 2. And it's in the products in both cases, so it does not cancel out. So we have NO2F. So, if we look at this chemical reaction, let's double check that everything cancels out. Okay, so we have 2 nitrogens on the left, 2 nitrogens on the right. 4 oxygens on the left, 4 oxygens on the right, 2 fluorines on the left, 2 fluorines on the right. So this is a good balanced chemical reaction. Whenever we look at this, the intermediate would be F. Okay, and if we were going to determine the molecularity of each step, well, in step 1, how many molecules collide with each other in the reactants? Well, step 1 is bimolecular. And then if we look at step 2, well, there's, again, another 2 molecules that are colliding with each other, so it too is bimolecular. So we can actually use these elementary reactions to predict rate laws. So we use the coefficients initially to look at rate expressions. So remember whenever we looked at the change in concentration over the change in time, and we would put 1 over some sort of coefficient. Okay, so that would be a rate expression, but then whenever we started talking about rate laws, we said, well, now we can't use those coefficients. Well, now that we're talking about reaction mechanisms, if it's an elementary step, we can still use the coefficients again. Okay, but for overall reactions, if it's an overall reaction, you do not use the stoichiometric coefficient. So, for instance, if we look at a unimolecular process, how will you know if it's an elementary step or not? Well, it's going to have to tell you somewhere that it's an elementary step. So for this decomposition of ozone right here, if we were going to write a rate law, we would say rate equals K times the concentration of O3. So now let's look at a biomolecular example. So our mechanism is we have A plus B going on to form products. So we would just go ahead and say, well, the rate is equal to K times A times B. But this has to be an elementary step. If it's an overall step, you can't look at the coefficients and write your rate law from it. But if it's an elementary step, you can. So here's a few examples. If you have A going on to form products, unimolecular, so you'd write rate is equal to K times A. Another way that you might see this written, instead of A plus A going on to form products, you might see this written as 2A going on to form products. So here, our rate law would be equal to K times A squared. So we would take that coefficient, again, because it's an elementary reaction. A plus B is a bimolecular reaction. So here you'd have rate is equal to K times A times B, because it's first order with respect to A and B. Then these are some more uncommon examples, but A plus B or 2A plus B. This is termolecular. So you'd have a rate law of rate is equal to K times A squared times B. So let's go ahead and try to write the rate law for the following reaction. So why don't you pause the video and then try to write the rate law for these three really quick. Oh, you're back. So for the first one, we might have rate is equal to K times, well, now we have O3 times O. For the second example, you probably got rate is equal to K times concentration of Br squared times concentration of argon. That right there is definitely a square sign. And then this bottom example here, this is one whole compound. So although this looks really long, this is just rate equals K times the concentration of some sort of cobalt cyanide, which I'm sure that would probably kill you. But it's a hydrated cyanide. Okay. It would just be to the first power, because there's an implied coefficient of 1. So, the first example, this one is a bimolecular elementary reaction. The second is a termolecular interaction. And the bottom one is a unimolecular interaction. All right, so now what we need to do is figure out how to calculate the rate law for overall reactions. So what we'll find here is that reactions occur in 2 or more elementary steps many times, but one step is always slower than the other. And what we call this step is a rate determining step. So if you were going to think about at a track meet, if you had a 4x400 team, your time is always going to be determined by the slowest person. They are going to limit how fast you run that race. So just like in track and chemistry, you always have a rate determining step. And this will limit how fast the reactants can be converted to products. So what we'll do with these rate determining steps is we are going to write our rate law based off of them. So here we have this reaction again, NO2 plus CO yields NO plus CO2. So what is the rate law predicted by this mechanism? Well, here we're going to base it off of our rate determining step. We would write rate is equal to K, so our rate constant, times NO2 squared. Okay, well, here's another sample reaction for this. Okay, so this is a three-step mechanism that has been proposed for another reaction. So we have NO plus H2 yields N2 plus 2H2O. So what's the rate law predict here? Well, the first thing we want to do is identify what our rate determining step is. So we'll always be given a step number, and then we'll be given a relative speed. So if it says slow or rate determining, something like that, that's the one that you want to write your rate law off of. So here, we'll go ahead and write, we have rate is equal to K times N2O2 times H2. So that's our rate law that's predicted by this elementary step of our mechanism. So we're always going to write it based off of the rate determining step. Okay, but there's a problem here. So we predicted this N2O2 times H2. And the reason why I put a subscript 2 here, K sub 2, that is just to denote that it is from the second step of the mechanism. So, can our rate law contain intermediates? The answer to that is no. We do not want intermediates in our rate law because we want our rate law to be based only on reactions or products. So only something that is in the overall reaction. So if what we have here is the experimental rate law is actually, the rate law is K times NO squared times H2. So how are we going to get this rate law? Well, we have to make an approximation. And this is known as the steady state approximation. Okay, so in the steady state approximation, what we're going to do is, let's look at this first step. This first step is fast and reversible. So what that means is that, let's write rate 1 for the forward reaction. So we'll denote that with a subscript of 1 and then F for forward. Then we'll write K sub 1 for the forward reaction. It's going to be NO squared. So we're looking at the rate for going forward here. But if it's fast and reversible, that means that this reaction also goes backwards. So the rate of that first reaction going in the opposite direction, which you might see denoted as K sub negative 1. So I'm going to go ahead and take off this F up here. We have K sub 1 for the forward reaction, K sub negative 1 for the reverse reaction. And this will be equal to N2O2. So in a steady state approximation, what we're saying is that the forward rate is equal to the reverse rate. Now what that allows us to do is to set these two terms equal to each other. So we can go ahead and write k sub 1 times NO squared is equal to k sub negative 1 times N2 O2. Now, we just said that we can't have an intermediate in the overall rate law. So what we need to do is we need to substitute that term out. So let's go ahead and solve this expression down here for the concentration of N2O2. So we have N2O2 is equal to K sub 1 divided by K sub negative 1 times the concentration of NO squared. And since K sub 1 and K sub negative 1 are both constants, we're just going to kind of package them together into a new rate constant. So we can write this expression here. So now what we can do is we have the concentration of N2O2 is equal to a rate constant times NO squared. We can plug into our initial rate up here for that. So now what we'll have, plugging into this expression right up here, we'll have rate, and we'll keep using both of these rate constants here. The rate is equal to K1 times K2 divided by K sub negative 1. Now remember we substitute in for N2O2 with this. So we'll have NO squared times H2. And then since what we have down here, all these are rate constants, we're going to package them into one. So we'll say the rate is equal to K. So that K represents K1 times K2 divided by K sub negative 1 times NO squared times H2. So now we are able to obtain the experimental rate law by using that steady state approximation for the forward and the reverse reactions being equivalent. Okay, so this is now a good mechanism because we don't have any intermediates in our overall rate law. We match experimental data, so we could essentially say that this mechanism is a possible mechanism at which this reaction occurs by the NO2, or the NO plus 2H2 plus N2. One of the next questions you might ask yourself is, do we need to consider any elementary reactions after the rate determining step? The answer is no. Only what occurs before or at the rate determining step will affect the kinetics, because anything after the rate determining step would more or less consider to be instantaneous. Here's one more example that I'd like you guys to try on your own. In this example, you might even end up with a product in your overall rate law. Just make sure that you don't have any intermediates in your rate law. Alright, so that will conclude our talk on mechanisms. And next time we'll finish up our unit on kinetics, talking about reaction rates with relationship to the collision theory.